Our topic for today is conservation of angular momentum, and we actually have two different really cases to consider for today. And one is the conservation of angular momentum when you have a single object changing its own mass distribution, and then you have the cases of conservation of angular momentum between objects in a collision. So just looking at the theory, for linear momentum, we said that net force times the change in time is equal to the change in momentum. So basically, if there is a net force on the system of objects, then there will be a change in momentum. So a key point here was that this is actually the net external force will cause a change in linear momentum for the system. If your forces are only internal, so for example, if I had two balls that were colliding with each other, and at least in the x direction there's no external forces, and in the y direction there's normal force and gravity, which are both external, but they're equal and opposite, so they cancel out. This would have no net external forces, so therefore the momentum of the system would be conserved. But the force here, maybe of 1 on 2, would times the time would cause a change in momentum for object 2, and then the force of 2 on 1 times the change in time would equal the change in momentum for object 1, but the change in momentum for object 1 plus the change in momentum for object 2 would still have to add up to 0, because f of 1 on 2 and f of 2 on 1 are internal to your system, so that the change in momentum for the system would still have to equal 0, because the sum of the net external forces was 0, because all the forces that were present would have been internal forces. So that was what we did for linear momentum. So the same thing's kind of true for angular momentum. So the difference here, though, is just that our objects, we can have like multiple objects or single objects that we're looking at, because our net torque is going to be I times alpha times our change in time is equal to our change in angular momentum. So the change in angular momentum is going to point in the direction of alpha, because alpha is the only vector here in that equation. But basically what this tells us is it tells us that basically we have more factors that can come into play. That we can have changes in our rotational inertia. So you're going to see situations where, like, you have like a person, like an ice skater or something like that, someone like on a rotating platform that has like low friction, that if they have, or like maybe holding something and they have some sort of rotational inertia I, and they're going to have some sort of angular speed associated with it, they're going to have some sort of angular momentum, and that if they pull in their arms, like an ice skater doing a spin, then what's going to happen is their angular speed is going to increase, because their moment of inertia decreased. We're going to still end up with no change in angular momentum. Or you can have options where things are just rotating. So like, say I have a rotating disc here that's on some sort of like axle. Okay, so that it's rotating with some sort of omega. And then I'm actually going to have a collision. I'm going to put another rotating disc here onto that same axle. Maybe it's actually at rest. And then I'm going to drop it on top so that they are stuck together, and then they're rotating, and now all of a sudden you have an increase in mass, essentially an increase in rotational inertia, as those two have collided, so the system is going to have to be rotating more slowly. Those are kind of some situations you'll see. The other situation that I really enjoy, that's kind of common, is they'll do like merry-go-round type situations. And so say you have a merry-go-round where this thing is rotating with some sort of angular speed, and I've got someone like standing here on the merry-go-round. Well, they can walk on the merry-go-round. If you played with it, you know, with any of those kind of merry-go-round type situations like in a playground where like they have handles on the outside and you can spin it up and then you can jump on and you can spin with it or whatever. So like if I was to walk kind of towards the center, just the act of walking towards the center is going to change the speed at which this platform rotates. And that's because you can treat yourself standing out here as a point mass, which has some sort of rotational inertia based on this radius. And that as you get closer, your new radius is smaller, so you're decreasing your moment of inertia. And because the only forces are internal to like you and the rotating platform, you're going to have angular momentum being conserved. So if you're getting decreasing rotational inertia, this thing's going to have to speed up in order to maintain the same angular momentum. Whereas if you actually were to be here and were to say walk in a circle, so if you were to start walking in a circle, in that case, you're maintaining the same radius r. So even though you're walking in a circle, in that case, you're not changing your rotational inertia in any way, shape, or form there. And the idea is that you are able to do that because you're actually applying a force kind of backwards on that, and that object is applying an equal and opposite force forward on you. Those are internal to the system. But because your moment of inertia isn't changing, then this thing's basically just going to maintain it's kind of the net motion for the system. So, but if you're moving that way and then the system is moving backwards, then you're still going to have kind of changes in the motion as a result, because you have to basically push backwards in order for you to move forwards. So the overall motion of the system still has to have conservation of angular momentum. So if parts of your system are moving in different directions, then the other part of the system is going to have to compensate in order to have that same kind of change in motion. So weird kind of fun things like that are going to happen. So you'll see those types of situations. You would start off with like some initial state and some final state. So what you need to do is you need to figure out what are the forces involved. If your net external forces, or not external forces, your net external torques are equal to 0, then your change in angular momentum is equal to 0. That is essentially the law of conservation of angular momentum. So you can have lots of internal torques, but as long as your external torques add up to be 0, then you're fine. And that's the thing, is I can have a lot of forces acting, but not all of my forces are going to exert torques. So it's not about on the total number of forces, it's about on the torques being exerted by those forces. And then what I would do is, if I've established that there are no external forces, then basically this change in angular momentum equals 0 means that my angular momentum at the start has to equal my angular momentum at the end. And then if it's a one object system, I might just have I1 omega 1 is equal to I2 omega 2. So for example, with the case where the skater or the person on the rotating platform pull their arms in, they have some sort of initial moment of inertia, and then as they pull their arms in, they're decreasing their rotational inertia, which would then cause their angular velocity to increase. So that you would have a conservation there. Or if I have a multiple object system, I might have angular momentum of object A, or I might have your moment inertia object A at the start, angular velocity of A at the start, plus angular momentum of object B, which would be I times B1 omega B1, and that's going to have to equal I A2 omega A2 plus I B2 omega B2. Okay, so this would be like for a two object system, where in this case I could either be changing my moment of inertia or my angular speeds during this motion in order to cause the other object to have some sort of change associated with it. So you could have lots more factors in this case. So whenever you're working these problems, the first thing you need to do is, first of all, identify is the net external torque equal to 0? And if it is, write that down, because like on an AP problem, angular momentum is only conserved if the net external torques are equal to 0. The same thing was true with linear momentum. Linear momentum was only true if the net external forces added up to 0. And so you should always write that down first. And then if that's true, define the fact that your change in angular momentum is 0, your change in linear momentum is equal to 0. And we're going to look at cases tomorrow where you have both linear and angular momentum, where one may be conserved and the other's not, or they're both conserved, or neither are conserved. So you're going to have to essentially look at the external torques and external forces for both cases. And then once you have that done, start off with some nice simple statement, substitute in the relevant variables, do all of that non-numerically first before any substitution in numbers to make sure that you are covering your basis. So those are the types of example problems that you might come across.